Case Western Reserve University's Institute for the Science of Origins proudly presents the Origin Science Scholars Program. The Institute advances the scientific understanding and application of origins and evolution of human and natural systems. The Origin Science Scholars Lectures are presented with the assistance of Case Western Reserve University's Siegel Lifelong Learning Program, College of Arts and Sciences, and Media Vision.
Tonight it's my pleasure to welcome Corbin Cobalt, Professor and Co-Chair of the Department of Physics at Case Western Reserve University, who will talk about intelligent life on other planets. What are the odds? And this is obviously presented in collaboration with the CWRU's Emeriti Academy. To quote Professor Covault, ever since humans began turning their eyes to the heavens, the question has persisted, is there intelligent life out there? Since dozens of Earth-like planets have since been identified, are we getting close to answering that question? What are the odds? Please welcome Professor Cobalt, who will enlighten us on the program.
Thank you, Chris. I'm delighted to be here today to talk to you about extraterrestrial intelligence. This is the first of what will be 2 lectures on the topic, and I will say at the beginning that this is a field that I've fallen into sort of accidentally over the past decade or so. My primary specialty is experimental high-energy cosmic ray astrophysics, but the techniques that we use for astrophysics can also be used to address some of these questions. There are others who are more technically capable and perhaps philosophically insightful than I will be on this topic since I'm relatively new to the field. But one of the great things about being a physicist is that you're taught to be fearless and to dive into new topics and to see what you can figure out. So I will share with you at least what I've figured out on this subject today. So what are the odds? So the reason this is an interesting question, of course, is that when you're in a situation where you have to make a decision, you'd like to know what's really going on, and often it is the case that you don't have perfect information. For example, if you were in Las Vegas playing a dice game and you had a situation where in order to win the game you had to roll an 11, you would be interested in knowing what are the odds of doing that, so that you have a sense of what the decision that you should make ought to be. Shall you invest your time and money placing a bet when the odds of rolling an 11 are calculated at 6% based on fair and accurate dice, or is that a bad idea depending on all the information that you have? So this is the kind of question where it's good to know what are the probabilities. And so we can ask the same kind of question if you're going to invest time and energy, money and effort to search for an extraterrestrial intelligent civilization that might exist, that we could in principle detect in our galaxy, in our universe. Is it worth the time and the money and effort? What are the probabilities that you would actually have a chance of succeeding if you started this endeavor? This is a picture of Jill Tarter, who's leads the SETI Institute and an array of telescopes at the Allen Telescope Array. And to address the topic, I'm going to use as an exploratory tool something called the Drake equation. This is an equation that was put forth by Frank Drake in 1961. And I know this is the Origin series, and we're not going to want to get too much into technical details of equations, but I want to basically point out that this is a particularly amenable and generous equation to tackle. It's basically an equation where you have something on the left-hand side which you want to know, which is the predicted number of detectable intelligent civilizations that we might be able to see in our galaxy, and on the left, and then on the right are just a whole bunch of terms that we multiply together. So no difficult algebra, no square roots or powers or weird things, just a whole bunch of terms that we want to multiply. So I'd like to basically walk through this equation as a mechanism to try to get a handle on whether or not we can talk about what the odds are of detecting intelligent life. So the first term in the equation are stars, just the rate of star formation. And it's basically a term that relates to the how many stars are actually in our galaxy. So the Milky Way galaxy, we now know, we've known for quite some time, contains at least 100 billion stars, probably closer to 300 billion stars. Most of those stars are red dwarf stars, stars that are smaller than, dimmer than our sun. But at this point, based on the details of the astronomical observations, we have a pretty good idea of what that number is. Another term, the next one next to it, is the fraction of those stars that have planets. And if you want to detect intelligent civilization and you assume that intelligent life develops on a planet such as Earth, like Earth, you want to know how many stars actually have planets around them. And the amazing thing is that in the past 10 to 20 years, we've really pinned down the answer to the question about planets. This is a artist rendition of NASA's Kepler telescope satellite, which was operated for just under 10 years. And it was specifically designed to be in space to observe observe stars in our local area, to look for evidence that those stars have planets around them. And to date, amazingly, over 2,600 exoplanets have been detected, most of which have been observed by this particular satellite. And based on these observations, you can be reasonably confident that it's the case that most stars have planets. So instead of planets being a rare and unusual thing, we've now confirmed that planets can be found all over our galaxy. Of course, now there's a new satellite out there that NASA has put out, the TESS satellite, which will again operate for several years, and it's expected to expand the number of detectable exoplanets seen by us into the 20,000s or higher. The new data is already coming in from TESS. The primary technique we use to detect exoplanets is the one of essentially a small eclipse, occultation, as the planet moves in its orbit. For those planets that are where the orbital plane is lined up with the visual line of sight, so that the planet goes in front of the star, it blocks a small, tiny fraction of the light. And you can see a small dip in the brightness as the star moves, as the planet moves in front of the star. Of course, even though we've seen well over 2,000 exoplanets, we'll call them, the planets outside our solar system, the question really is, well, how many of those planets could in principle harbor life of some kind? So you kind of define a habitable zone as a planet, as a region near a star where a planet in that region would have, say, liquid water, and the planet would not be too big, not be too small. Something like Jupiter or Neptune is too big and too far away from our sun to harbor life. But planets such as Earth and Mars maybe could be candidates for the development of life. And to date, they've detected over 21, over 20 so-called Terran exoplanets, planets that are not that different from Earth's size and mass, in regions where in principle liquid water could be stable, so that the planet's not too close to the sun and not too close to the star and not too far from the star. So you then extrapolate the results that were seen by Kepler satellite and TESS. Of course, not all planets line up, so then you basically ask what are the probabilities, and you end up that virtually every star in our Milky Way has a reasonably high chance of having at least one planet, and some reasonable fraction of them could be so-called habitable planets. And then if you insist that maybe it's more likely to have life in stars that are yellow and not red. Within our local neighborhood, there's anywhere from 2 to 9 solar-like stars with planets on them that could, in principle, be compatible with the existence of life. And then when you expand to our whole galaxy, you're talking hundreds of millions or maybe even billions of planets that are similar enough to Earth where life could, in principle, form. So that's where we are now. Most stellar systems have at least one planet. Many of these are Earth-like, and therefore, at least within our galaxy, many millions of Earth-like planets. And today, 2019, these terms, these first three terms corresponding to this information in the Drake equation are all well known, which is to say they're known to within, say, an order of magnitude of 2. The next term in the Drake equation is the fraction of planets in which life spontaneously or otherwise arises. So how many planets do we think actually, how likely do we think it is that a planet that's out there will have life on it at some point in its history? And the estimates of this term are, well, wildly speculative. We don't know. The next term is the fraction of those planets with life where intelligence arises. Of course, we have to define intelligence. But then even having done that, the estimates of this term are wildly speculative. Then there's a question of what fraction of those planets does the intelligent life develop in such a way so that what we would call a technical civilization capable of sending an interstellar signal to us so that we could actually talk to them. What fraction of those are there? Again, estimates of this term are wildly speculative. And then, of course, an interesting term is, of course, the average lifetime relative to the star formation rate of a civilization. Our civilization has only been able to send technical information out to other stars, at least in principle, on timescales of decades, if not quite a century. Maybe the average lifetime of technical civilizations are short, maybe they're long, maybe they last for hundreds of years, maybe they last for millions of years. Estimates are wildly speculative. So the Drake equation is not yet solved. It basically helps us separate our knowledge from our ignorance. The terms on the left are much more certain than the terms of the right. We do know we have many stars, and now we know, only in the past really decade, that we have many planets. But we don't know whether those planets have life on them or civilizations that can achieve technical communication. We only have one planet to study, and that's ours. So the good news is we've now made these new observations, and the case for extraterrestrial intelligence has never been better. Now we know that there are all these planets out there. But the bad news is we still have a very uncertain estimate of these odds.
Is there any thought that if there is life on exoplanets, that it might be supported by chemicals or elements other than what supports life here on Earth?
The question is if we, for example, you could imagine in principle a chemistry, a biology, an ecological system where instead of having a water-based ecology with organic carbon-based molecules putting together to systems that are similar to our own, that you could have something completely different that we would not necessarily recognize as life like ours. And in principle, such life could be evolve and communicate with us. Yes, that's definitely a possibility. So if you add the possibility that technological communication could arise from, say, a different kind of biochemistry, or maybe technological civilization could arise from a different kind of life altogether. Say, life not as we would call it normally, but maybe technical, robotic, or some other kind of form of life that we've never even been able to imagine. Then, in principle, that would raise the odds. But we don't know. We don't have any evidence that is true. We've not yet detected a single place where the carbon-based life exists outside our planet, so we don't know.
You've given us the Drake equation, of which half of which is wildly speculative.
Wildly speculative.
Is this the only equation that we have, or the only algorithm to kind of figure out if there's life, or is there another algorithm or another formula?
So the question is, if I were smarter, or somebody was smarter than Drake and came up with a different way of doing this estimate, maybe we would come up with a better way. I am aware of one variation of the Drake equation, which is called the Archeological Drake equation. And this is a calculation where instead of estimating what the probability of that we can detect a civilization is right now, you estimate the probability that any civilization ever existed in our galaxy. And this basically compresses several of these terms into one term. And you could argue that in some sense where this is a better way to go, since you have, instead of many uncertain terms, you only have one or two uncertain terms. but they're still wildly uncertain. So to the best of my knowledge, there's not a better way of at least articulating the regions within which we have knowledge versus ignorance.
How does one determine if a planet is in a habitable zone?
That's a good question, and in fact, it's a question that is not easy to answer as far as my understanding of it. What you do is you actually ask the question, what is the average amount of energy that's deposited onto the surface of the planet based on the approximate position of the planet relative to the star. So when you detect the planet using this occultation technique by repeated measurements and by measurements of the brightness of the sun and inferring the temperature of the sun, you can get a rough estimate of the orbital parameters for each planet that you see. And then based on that, you can calculate, well, how much sunlight is falling on the planet, and therefore on average, what would the temperatures be on that planet? These are very rough calculations. And when you do this, you can basically make predictions for what the probability is that water will be, at least sometimes in some places on that planet, found in a form that's neither frozen nor gaseous, which is to say steam, but water. Having said that, when you actually ask the experts, well, how big is that region, and can we all agree on what that region is? It's quite broad. But for example, in our solar system, in principle, Earth and Mars fall into such a region, and Venus barely doesn't, at least to some calculations. So it's a broad swath. And then, of course, in real life, if you're not really in the sweet spot of that region, it may or may not be easy for life to develop as it did, say, on Earth. Yes.
Are there plans, any satellites, for instance, that will take a closer look at some of these more likely planets?
I'm going to talk about that a little bit further into the conversation. I mean, one of the challenges, so the great benefit of the occultation eclipse technique is that you measure just a signal, which is the brightness of the star, and you can infer all of these parameters. But you're not looking at the light from the planet, you're looking at the light from the star. And that doesn't tell you anything directly about the star, about whether the planet itself looks like it's a habitable planet. Does that planet atmosphere have oxygen or something like that, for example? How thick is the atmosphere, and therefore, based on that, what really is a good estimate of the temperature? And so, yes, there are initial attempts coming up in the next decade to try to get at the question of detecting the planets directly, as opposed to inferring their existence indirectly. But it's very challenging.
Thank you for joining us. You've been watching Corbin Cobalt, discussing the Drake equation, which lays out what we know about the probability of intelligent life on planets around stars other than our sun. For more information on the Origin Science Scholars Program, please visit the Institute's website at origins.case.edu. In the next part of the talk, Professor Covault will discuss Fermi's Paradox. If intelligent life is common, why haven't we encountered it? Now, back to the talk.
So the next part of the talk I want to, so we've looked at this, we've basically calculated the odds, and we have an answer that is what we call wildly speculative. When you multiply well-known numbers by unknown numbers, you end up with an unknown number. But it doesn't mean we know nothing, and I want to introduce one of the things we know from a famous physicist, Enrico Fermi, who developed the first atomic nuclear reaction pilot at the University of Chicago. And in the 50s, he was sitting down with some friends, and he introduced this question, which we now know today as the Fermi Paradox. And so I want to take a minute to kind of explain how the Fermi Paradox works and what it might or might not tell us about the nature of extraterrestrial civilizations. So the basic idea is that our universe has been around for a long time. The Big Bang started a little over 13 billion years ago. The Earth is a relatively young member, the solar system is a relatively young member of the galaxy's population. The galaxy itself is a little over 12 billion years old, and so there's plenty of times. Most stars in our galaxy were created billions of years before the Earth. So in principle, there could have been a planet that appeared on that one of those stars that was born before ours, where life in principle could have developed billions of years before our own. And then the question is, suppose life on that planet had developed a technology that we would call, say, foreseeable, not what we have today, but maybe in the next 100 or 200 years. So for space technology to very slowly and very deliberately explore the galaxy by sending out self-reproducing robot probes that basically hop from star system to star system in search of information about the universe and in an effort to basically spread the technology of that civilization. What would happen? So there's a nice image here that I got from Professor Schomburg at the University of Oregon. So, for example, if you have a light sail or some technology that you could imagine having on the Earth in the next century or two, and you sent a probe to the nearest stars, moving at a speed that was a tiny fraction of the percent of the speed of light, it could take hundreds of years for that probe to get to the nearest star, or two. Maybe, let's say 500 years for round numbers. In 500 years, this Planet X society would get probes to the nearest 2 stars. That's step 1. And then if you wait 2,000 years, well, of course, each of those probes is intelligent, artificially intelligent. It basically designs a technique for reproducing itself based on the raw materials around those stars. And then in another 2,000 years, due to geometric progression, you're up to, say, 32 stars. So it's 2,000 years and 32 stars. And 2,000 years is a long time for you and me. We wouldn't want to wait around for stellar exploration at this rate. It would be pretty boring and slow. But nonetheless, you get up to 32 stars in 2,000 years. And again, geometric progression. Now each of those stars has probes that are launched further out into other nearby stars. And after about 3,500 years, you're up to 256 stars. In other words, powers of 2 just keep multiplying. And so forth and so on. You only have to wait about 5,000 years and you're already up to over 8,000 stars. Now 8,000 stars is a tiny fraction of the stars in the galaxy, but nonetheless you're growing geometrically. What happens when you basically let the thing go? The probes continue to expand and explore the galaxy. How long will it take to get probes to all 100 billion stars in our galaxy? The answer is, because of the geometric effect, it will take about 4 million years. 4 million years for probes to get all the way through our galaxy if they were continually colonizing, using resources, and expanding on a geometric progression. And the key issue is that 4 billion years is tiny, 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 tiny compared to the age of our galaxy. Right? If this Planet X was several billion years before the Earth, then many billions of years before we came into existence, the entire galaxy would be populated by these robotic probes. 4 million years, that's, I mean, I'm reminded, that seems like a long time, but you know, the Lucy display outside says that she was here 3.2 million years ago. So even within the realm of human existence, you could basically, hominid existence, you could basically populate the entire galaxy if you had a civilization. So the question is, if that's true, where are they? Where are all the probes? Where's all the communication from this original civilization that was here before us? And Fermi basically pointed out that there's nothing there. We don't see evidence of such a civilization. So this is called a paradox because, of course, you just make this basic assumption, you get a contradictory result. What are the resolutions of the paradox? And there's lots of ideas for how to resolve the Fermi paradox. Many of them relate to a concept which you might call the great filter, which is to say the supposition, and again, it's just that as intelligent civilizations, a species advances from basically, pre-life chemicals to a civilization that basically lives in the entire galaxy. There are key milestones for the development of that civilization. And some of them are easy to get through, corresponding to these yellow lines. But as you move through time, going from the left to the right, perhaps there's one barrier that corresponds to a really difficult challenge to overcome for the development of technological life. And that barrier means that virtually all species that hit that barrier either stop or die at that point. And it's only on rare occasion that a tiny number of those civilizations persist to go on to expand to populate the galaxy. It's an interesting idea. And of course, once you put it out there, then there's two possibilities that are worth considering. The first possibility is that the great filter is in our past, right? In other words, our civilization is developing from the left to the right. And the first possibility is that we've already gotten through the great filter. Maybe, and of course, you can speculate on what that filter in the past might have been. Maybe the spontaneous formation of life, what you would call abiogenesis, maybe this is extremely rare. Maybe the probability of life forming could be astoundingly tiny, 1 part in 10 with 100 zeros on it, or something like that. Maybe life is ubiquitous, but the formation of multicellular life, which appeared relatively late in Earth's history, is exceedingly rare. Maybe, in relation to a question that was asked earlier, maybe even if a planet is habitable, maybe there's a whole series of special conditions that have to happen just so that life can basically develop over a 4 billion year history, such as we have on Earth, that are extremely unlikely in other places in the galaxy. We have the moon, which has tides. We have a planet sweeping Jupiter, all kinds of possibilities that basically boil down to the prospects that we are very, very lucky to have arrived to where we are, and that we've gotten past the great filter that stops life and the development of civilization in the past. So we're past the filter, phew, okay, and on we go towards galactic civilization. Now, it's worth stopping for a second and pointing out, are we really lucky? Is this really a plausible thing? And how likely is it that life can develop to the point that we're at based on our experience that we already have? And I want to argue that the fact that we're here and that we observe ourselves being on a planet that is teeming with life, multicellular life with technical intelligence, that's the intelligence I'm going to talk about today, not other kinds. The fact that that is true tells us nothing about how likely it is for that to occur on any other planet anywhere else under any other conditions. And the reason it tells us nothing is what I call the weak anthropic principle. It basically has to do with this logical idea. You think, well, we're typical. You say, we made it to this point. Why wouldn't this happen someplace else? But the fact that we made it isn't useful information, because if you assume the opposite, you end up with a contradiction. If you say, well, we made it and we find ourselves on a planet where life actually got to this point. But then if you say, well, let's assume that we're making the observation and we're sitting on a planet where life didn't exist, where life either didn't get going or unicellular animals, multicellular animals didn't develop, or intelligence never happened. But we'd never make that observation, because by definition, we are in at least one place where this condition is met. So the fact that it happened to us doesn't tell us whether it's likely to happen to anybody else. It may be profoundly unlikely that where we are and where we're at occurred. It could be very unlikely, but it did occur, and the reason we know it occurred is because we're here. So another possibility is that the great filter, the one that basically keeps us from noticing all of these other civilizations, could be in our future. And there's lots of ideas for what the nature of this filter could be. Maybe technological civilizations are bound to self-destruct. Maybe mass extinctions are waiting, gamma ray bursts going off, or some other natural or astrophysical phenomenon. Maybe, and this is a kind of scary idea, maybe there is a technological civilization that beat us to it, and they're out there, and one of their philosophies is that they aren't going to let anybody else come up besides them. So as soon as a species meets a certain technological threshold, they're called whack-a-mole. They're basically taken out. Another possibility is that this exponential growth model is not actually a realistic way of predicting how a species will colonize a galaxy, that issues of resources and sustainability constrain that growth, and so therefore basically we don't expand because we basically slow down and stop. Or there could be something in the future that awaits us that we have no idea what's coming, a fatal problem that we can't even predict now. So if that's true, well, we got to worry about that in the future. There are lots of other ideas to explain the Fermi Paradox, besides the filter idea. Where are they? One answer to the question is, well, maybe they are here. Maybe there are probes all through our solar system. We just haven't stumbled on them yet. They're hiding or buried or otherwise invisible to us. Maybe they were here in the past. Maybe they've been here multiple times in the past, but we have no evidence of that. Maybe we've looked not long enough or deep enough. Maybe we don't know what to look for. Another idea is that we don't see the rest of the civilization is because we're put in a zoo. We're basically being told, basically in a situation where we're basically prevented from seeing what's outside of our solar system in terms of technological civilization, so as to benefit our natural development or something like that. And there's even crazier ideas, such as reality is not really real. We exist in a computer simulation. There's some kind of growing thing. Maybe they that came here are us in some sense of the word. And it's worth remembering as we address this issue that in terms of what we know about the existence of civilizations, we've barely looked beyond our nearest neighbors. If you see a little red dot there on the surrounding a blob of stars in what would be a drawing of our Milky Way, a whole night sky basically could be wrapped up in that tiny little dot. We've only barely begun to look into the galaxy to know what's really there and what's really typical. Maybe our neighborhood is not typical. Okay. So I'm going to stop there, having talked about the Fermi Paradox.
Some of the fictional writings, like Eric von Däniken, talking about some of the markings on Earth being made by space visitors. You want to comment on that?
First of all, let me reflect a personal fact, which is I'm a lifelong fan of science fiction and the idea of sort of thinking speculatively about what if possibilities having to do with aliens coming to us in the past and the future, how they could have snuck in, how they might have affected human history. It's a really interesting idea and lots of fun to think about. But every time you look at one of these things, it's, how can I put it? It's not that difficult to come up with plausible explanations for what you see that correspond to either natural phenomenon or historical reality of the development of animal species and then our species and prehistory and so forth. So as far as I'm aware, and based on everything I've ever seen, there's not a shred of definite compelling evidence that such a visitation has taken place. But having said that, the Earth is 4 billion plus years old, and alien species that could have appeared to us in the distant past, the evidence for that could have been easily washed away. It might be very difficult to find, especially if they were careful about not leaving their tracks too deeply. So we don't know. We just don't know.
What can you tell us about the Nazca Lines?
About the what?
The Nazca Lines.
The Nazca Lines. Tell me what I'm not sure I know what you mean by the Nazca Lines.
They are geometric figures in northern, I think it's Chile.
Right.
That virtually impossible to be seen except from the air. No explanation where they came from, how they were made, and they've been there, as far as we know, for thousands of years.
Right. So you're
on the driest part of the Earth, and they're still there.
Right. Okay.
So I'm convinced it's aliens.
Well, I won't tell you that it's implausible that they're aliens. It is plausible, right? But because we weren't there, that evidence is, I'm calling it very indirect, yes? We tend to think of past civilizations in the context of our own. I am not an anthropologist. That's a very challenging job. And there are all kinds of things when we look deeply at what we've seen in the past that are surprising and interesting because we only have partial knowledge of what's going on. So I would say those are interesting results, but I don't find them compelling. How's that?
Are we trying to develop a way of actually looking at exoplanets and determining from chemical signatures whether or not the conditions are right? Do we have any capability in that direction at all right now, and are we looking that way in the future?
The answer to your question is we have no capability of that right now, but we are definitely looking to that direction in the future. So I'll highlight two things. One is that the James Webb Space Telescope, which is the next major telescope that's going up, it will barely be able to tackle that issue for some of the bigger planets and some of the closer stars. The main issue is one of contrast and tiny, tiny size of planets compared to size. So we're talking easily 10 to 100 billion times brighter the star is than the planet. Having said that, some very clever people are working really hard on new ideas for that. If you, last week, Ben Monreal gave a presentation about one of his ideas for a giant telescope that would tackle that issue. But it's clearly the next major thing, and that's where I'm going to go with the last part of my talk.
Are binary stars in any of this investigation?
As far as I'm aware, it seems to be the case that binary systems are at least not wildly unlikely to have planets as well. In other words, according to the Kepler results, some binary systems, not really close binary systems, but spread apart binary systems, clearly have evidence for planets as well. So that may be part of the calculus too. What gets interesting is whether you can make the case where a binary system is either more likely or maybe less likely to be hospitable for the development of life. I think that's a challenging question.
We hope you've been enjoying the Origin Science Scholars Program with Corbin Cobalt. Professor Covault is professor and co-chair of physics at Case Western Reserve University and a fellow of the Institute for the Science of Origins. In the second part of our talk, we discussed how evolutionary hurdles, called filters, might explain why we have not yet encountered intelligent aliens. In our final segment, Professor Covault will discuss what we have left to learn to answer the question, are we alone in the universe? Now, back to our talk.
The last part of the discussion I want to have is I want to bring, how can I put it? We started off by looking at the Drake equation, and we were quickly stymied by wild speculation, as we say. And then we looked at the Fermi Paradox, and that was intriguing because it highlights the fact that it's sort of surprising if you make naive assumptions about how civilizations should expand through the galaxy. The fact that we haven't detected it yet, at least not categorically, is sort of surprising. But before I turn to the question of SETI, the search for deliberate signals sent to the Earth or the vicinity of the Earth for the purposes of being picked up as a communication of information, I want to talk a little bit about how astronomy and astrophysics itself has developed over the course of the past few decades and will continue to develop to address these questions of answering what's going on with advanced technological civilizations. And to set the stage for this, I want to introduce an idea that was put forth by a physicist in Russia, Kardashev, that basically hypothesizes that the development of technology in a growing civilization scales so as to take advantage of the resource of energy. So if you ask the question, what is a plausible limitation on the capability of a civilization to develop? The answer is, well, how much energy resources can you sustain to support the activities of that civilization? So Kardashev basically developed ideas for three types of civilization, advanced civilization. Type 1 is a civilization that is able to harness the energy resources that are characteristic of an entire planet. Type 2 civilizations would be those that are able to harness the resources of a stellar system, a star. And then type 3 civilizations would be those that basically harness the energy reserves associated with an entire galaxy. And the question is, what can we say based on what we know about the universe based on these types of civilizations and what's actually going on? So here, for example, is an artist rendition of a Dyson sphere or a megastructure. Maybe you call it a Dyson swarm. It depends on how those pieces are interlocked. That would be maybe a kind of a science fiction idea of what a type 2 civilization would do. It would basically take material from its planets, rearrange them, manufacture a system where a reasonably large fraction of the energy output of an entire star could be captured on the inner surface of that structure. So this would be a structure whose size would be comparable to planetary orbits, and where obviously vastly advanced and superior compared to our own current technology. And what's interesting is if you talk about the existence of such megastructures, you can actually ask the question, is there astrophysical evidence for those megastructures? So for example, in a case of a star like this, where you basically have material blocking out some reasonable fraction of the light, you'd say based on the spectrum of the star, a star that's surrounded by a partial Dyson sphere or a Dyson swarm or some kind of megastructure would be dimmer on average, or would have variations in its light output as that structure moves around the star. And the Kepler satellite has looked at 20,000 stars. This is the same satellite that was looking for exoplanets. And it's, again, very capable of looking for changes and measuring the relative intensity of the starlight. And so far, it has no evidence for any stars that appear too dim. There was one star that looked like it might be too dim, but there was a calculation done in the distance of that star based on its parallax. And so far as we know, there's no evidence whatsoever, at least looking in our near solar neighborhood, for the existence of such megastructures characteristic of such an advanced civilization. Having said that, there are unusual objects out there, and the more we look, the more interesting and varied it appears our universe is. And this is not unsurprising. I mean, it's really not true that if you've seen one star, you've seen them all. Our galaxy is rich in diverse phenomenon. One of the most exciting results of the past few years has been the detection of an object known as Tabby Star. And Tabby Star had some very unusual variations in brightness over the course of observations of months and years, which were not easy to explain in the context of a simple model planetary phenomenon. But after a while, based especially on spectral observations of the measurement of the intensity of light as a function of wavelength, the idea that there was some kind of Dyson megastructure was ruled out, and now it looks like those variations are consistent with an unusual and irregular collection of dust lined up with the star, but not aliens. Another similar kind of idea of discovery was the detection of the asteroid or cometary asteroid, whatever you're going to call it, a very unusual object known as Oumuamua, which came into our solar system on a trajectory that clearly indicated that it does not arrive. It arrived from well outside our solar system, went through the system. It has a very unusual shape, much longer than it is across the dimension, based on the rapidly changing intensity. I mean, we never actually took a picture of it like this, anything like this. But again, this was such an unusual object that people thought, well, maybe this is an indication of some kind of technology. And even as this object was observed carefully, further and further, basically, it was consistent with an object that unusual, very, very, very strange shape, coming from very strange location, but nonetheless not aliens. So to get at the question of whether you can really get a handle on what's going on in planets, you really need better telescopes. And the next big generation telescope that will address this issue is the James Webb Space Telescope, currently, crossing fingers, planned for deployment in 2021. This is a very large mirror that will achieve unparalleled angular resolution and sensitivity to stars and everything that it could be used for astronomy and astrophysics. But in particular, this device will have barely the sensitivity, the angular resolution, to look for evidence of life by direct observation of planetary atmospheres. And of course, the hope and expectation is that the detection of life as an influence on a planetary system would be its impact on the atmosphere, the changing of an atmosphere, such as the way our atmosphere was changed on the planet Earth due to the prevalence of life and photosynthesis and so forth. So I want to go back to end. I want to basically go back to the Drake equation and sort of reflect on what we've learned and what we can expect for the future. Again, the values on the left-hand side, the rate of the star formation, the fraction of planets that are in the solar system, and the number of those planets that at least have the appearance that's similar to Earth, these values are increasingly well understood due to the recent advances in the detection of exoplanets. The next big milestone is the term F sub L, which is the value, the fraction of Earth-like planets where there's some kind of life as inferred by the direct observation of atmospheres and so forth. And my expectation, based on the development of new telescopes and a real push to try to directly detect these exoplanets, is that if it is the case that life is reasonably likely, which is to say that many planets where life could arise, there is life there, and that life propagates in such a degree that it influences and is detectable in the effects of the atmosphere, that's a question that we can expect to have results on over the course of the next, say, decade or two, at least if those results are positive. And if the results are not positive, then we'll know something about that probability because we have basically looked at worlds beyond our own. So far, we've looked at no worlds beyond our own for this particular issue, at least not outside our solar system. But tackling these terms on the right-hand side, having to do with intelligence, civilization, and the length of the likely lifetime of civilizations, these are much more difficult issues. We have to combine speculative assumptions. We have to basically go through exercises such as reflecting on the Fermi Paradox in combination with increasingly sensitive astronomical observations, and then plausibly, arguably, moving in the direction of actually searching for communications from these alien civilizations if we're going to tackle those last terms. So in conclusion, we have more scientific tools than we've ever had before to address this issue of what's going on in alien worlds. We now know that exoplanets are ubiquitous, and our tools are improving, and we have a definite path towards the next big question. Does life exist on other planets, and can we develop the technology to look directly at these atmospheres? But to date, and to make this very clear, we do not have any solid concrete evidence or information that would allow us to even approximately estimate the probability that advanced civilizations might exist within any region of space near us. We can't predict whether they're in the nearest 30 light years. We can't predict whether they're in our galaxy. We can't predict whether they're in the trillions of galaxies that surround our galaxy. There's no evidence yet to suggest that life exists anywhere else. We cannot yet scientifically calculate the odds. Nonetheless, just want to end the sort of quoting Arthur C. Clarke, a scientist and science fiction writer. Two possibilities exist. Either we are alone in the universe or we are not. Both are equally terrifying. You could say both are equally fascinating. I mean, obviously, it would be really interesting to know and to make understanding and to gain knowledge that other civilizations, that other life exists, that we are not alone. That would be really interesting. But it would also be interesting to confirm or conclude that we are unique. This possibility still exists. This is still a plausible scenario. Despite the fact that the planets are there, we still don't know if there's anything else out there. We still don't know if anyone else shares our universe on any scale with us. So now we don't know the odds. Shall we do SETI? I mean, it's like betting, making a bet without having any idea what the dice look like. We can't calculate the odds, but we can say that the probability of detecting alien civilization will approach zero if we don't even look for this communication. So that's where I'm going to go the next time we speak. I'm going to be here a week from now, and I'm going to talk about my own work and the work of others having to do with the search for extraterrestrial intelligence, and in particular the effort to detect technological signals that might be beamed to us coming from outer space, what that effort entails, what the assumptions are, what has been accomplished in the past, and where the field is going to go in the future.
I'm just curious what a professional has to say about crop circles. Is there any current explanation whatsoever?
I can't explain crop circles. I just can't do it. But I know a lot of people who can, or claim to be able to. And it seems to me that, how can I put it? When you point at something, you say, I don't have an explanation for this, but I'm happy to call it, but one idea that could be true is that it's aliens. This happens, and every time this happens historically to date, the deeper you dig, the more it seems that you can come up with an explanation, and it's not aliens, right? So for example, there was a recent paper talking about Oumuamua, where some astrophysicists from Harvard noticed that the object was accelerating away from us, leaving our solar system at a rate that wasn't consistent with simple gravitational attraction. And they hypothesized that perhaps Oumuamua had a light sail, it was an alien craft that was basically being accelerated by the light pressure from the sun. And that's plausible in the sense that you could say this is one possible explanation. But planetary scientists would look at Oumuamua and say, well, the asteroid comet is outgassing. We can't see the outgassing, but it outgasses in the direction facing the sun like other comets do. And this causes a momentum reaction that pushes it along, and that's also plausible too. Well, what's the way I want to put it? Extraordinary claims require extraordinary evidence, yes? Crop circles, is it a hoax? Is it clever people? Is it something else? I can come up with interesting but not extraordinary explanations for why crop circles exist. But for aliens to come around and mess with our wheat for no other reasons than for us to go, that seems like an extraordinary claim, and I'm not going to buy it unless I see extraordinary evidence.
So cockroaches have been around for a long time.
Cockroaches, yes.
And they're not intelligent.
Absolutely.
So what makes us think that if there is life somewhere else, that it evolves into intelligence and doesn't just become another cockroach?
What we do when we think about studying advanced civilizations is we make this completely unjustified assumption that other civilizations would be like us, and that the fact that technological civilization evolved on the Earth means that it's likely, or at least plausible, or at least not wildly unlikely, that it could happen elsewhere. But several people have argued that perhaps the development of an intelligence that that leads to technical civilization is much less likely than we think, because evolution itself is basically a blind and unintelligent process that leads to the species basically finding their survival of the fittest situation, and that may or may not involve intelligence. You're right, and we don't know until we have a chance to look at other worlds and see life as it evolves someplace else. We won't know the answer to that question, but it's entirely plausible. Intelligence is a uniquely human thing, and I'll talk about this in my next lecture. When we make assumptions about communication, we have to make the aliens want to communicate us. We have to make all kinds of intrinsic, what I'll call chauvinistic human society assumptions about how that communication ought to go. And those assumptions are wildly speculative, yes? And so with that, I'll thank you very much for your time and attention, and end my presentation.
The Origin Science Scholars Lectures are presented by Case Western Reserve University's Institute for the Science of Origins, with the assistance of the Siegel Lifelong Learning Program, the College of Arts and Sciences, and MediaVision. For more information on the Origin Science Scholars Program, including a full video archive, please visit the Institute's website at origins.case.edu.